Hi everybody, get on in here. It's time for GIS. So, we're at the end of week 4 already, and man, it seems like we're just getting started, but everything's on a compressed schedule this semester. So we keep moving forward. Almost to the weekend. Today, what I want to do is I want to give you guys a big hint on the lab practicum, a little bit of help, and I've the thing that I'm going to tell you to do. I've suggested that you do before, but I want to explain why you should do it, and I myself didn't fully understand the reason why you need to do this until yesterday when one of the students, Alexis, when she ran into a problem with visualization, and I looked into it a little bit. Okay, so then we're going to do a little bit of exploration of latitude, longitude, how it's represented as decimal, how it's represented in another way called degree, minute, seconds, and what's the connection. We'll talk a little bit about compasses. So these are like fundamental topics in using maps, and we haven't really discussed them in depth. So I think it's worth taking a little break and doing that. And if we have time, we'll do a little work with feature creation. We'll continue working with feature creation in ArcGIS Pro. All right, so let's do this. So got any questions? Put them in the comments, and let's turn it over to ArcGIS Pro, and time for that hint. All right. So I opened up ArcGIS Pro and I'm gonna start a new project. And I'm not going to bother naming it anything because I'm not really interested in keeping this project. But so you'll do something like this when you are working on your practicum. We'll do exactly this when you're working on your practicum. And I've already downloaded the files that I shared with you on Sakai into a folder on my local file system called data in this subdirectory. Okay, so it's there, and I'm gonna do. My window is too big. You can't see the bottom. Well, I can't see the bottom. You can. That's weird. Sizing. All right. There we go. All right. So we can both see this. So in my catalog, I'm gonna add a folder connection to that folder. And it is buried deep in my file structure, but I'll find it. It's in here. There it is. Okay, so I added that folder connection to my catalog. Here in my project, and I can right-click on this lab and practicum map package and add it to my map. Add and open. So this is how you're going to get started, and the when you're working with, so here's the big hint. Okay, you probably already figured this out. So these two data tables, adult smoker percent, lung cancer rate, I added those to my contents pane and add them to my current map, and then what I want to do is merge the data that's in my attribute table for US states with the data that's in these CSV files. And if you remember, the way you do that is with a join. You do a join. So I won't tell you the details of how you select the parameters there because we've done that before. But when you do this join, there's another thing called a relate, and I thought joins were permanent and relates were not. But it turns out when you do a join, so you're taking data from a table and joining it to an attribute table, that connection isn't permanent, which means there's been no modification to the underlying data that's producing the layer itself. So in this case, U.S. states. That data isn't modified at all, and the consequence of that is some of the symbology that you would apply to your map, including graduated symbols, doesn't work when you have that sort of temporary relationship between the data that you joined to your attribute table. So what I did before and didn't run into any problems, and I just did it because it's good practice to do so, not really appreciating that it would avoid this problem of not allowing you to accomplish the symbolism you want, was after I did the joins so that the data for the cancer information was joined to the US state data, I saved that layer as a new feature class in my geodatabase. And so what I'm saying is I went in here, right-clicked, did data, export feature, and then I exported it to my geodatabase, which should be in this folder right here. So it's empty right now because this was a new project. And when you do this, it's going to create a feature class in here of whatever you name it, and it'll add that feature class automatically to your map, so then you can go and you can remove this other one. But the main effect that will have is it makes the relationship that you created when you did the join permanent. It makes it permanently part of that new feature class. And then you don't run into any problems when it comes to adding the symbology to your map. Okay? So let me summarize that one more time. So the process of creating a join between data in a table and data in a layer on your map, in the attribute table for a layer in your map, is temporary. And there, for whatever reason, there's one of the shortcomings of that is it prevents you from doing certain types of symbology on your map, including graduated symbols. So the way to avoid that is to make the join permanent by saving the data in that layer as a new feature class in your geodatabase, which then will be automatically added to your map, and then working with that new layer and removing the previous one. All right. So hopefully that's clear. But this is a big hint, and it's going to avoid a lot of problems. And I didn't run into it when I was working through the various activities we worked on in class, because I always just do that step of exporting my data as a new feature class. But if you don't do that, you will run into this problem. So as a rule of thumb, if you're working with tables and you're joining tables to layers on your map, attribute tables associated with layers on your map, if you're working with shape files or anything that's not the native preferred format of ArcGIS, which is geodatabase files with feature classes inside of them, you should always convert them at the earliest convenience to feature classes in your geodatabase. Okay, and avoid problems. All right, gang. So that's all I got to say about that for now. Let's turn our attention to some of these other topics that I want to talk about because they're interesting and they deal with just general knowledge for using a map. And okay. All right. Okay, so let's talk. You guys know what latitude and longitude are now and you probably knew before this class, but now you definitely know what latitude and longitude are. And let's talk about the way that you represent latitude and longitude. I wrote long. Lat long. And we'll use a specific coordinates to talk through some of this stuff. So I actually looked this up this morning. In Shepherdstown, King Street kind of goes, I don't know, north-south-ish. And German Street crosses it. So at the intersection of those two roads, North King Street and West German Street, that's where you got, gosh, why can't I remember it now? What's the name of this building? McMurrin. McMurrin Hall is right here, and like the sweet shop is over here, and then there's that Chinese restaurant right here, and the War Memorial Book Building is right here. So it's like it's downtown Shepherdstown, and the coordinates of that intersection, the latitude and longitude are latitude of 39.430875 degrees north. So that's 39 degrees north of the equator, relative to, so the way, no, I want the webcam. Okay, the way you imagine this is, what are these angles telling you? There's a spot in the middle of the Earth, and you imagine a line going from the middle of the Earth, the center of the Earth, to a point on the surface. And the latitude of that point is the angle between that line and the equator. And the convention is, if you're going north of the equator, it's positive, and if you go south of the equator, it's negative. Okay, but and this is summarized in the Google slides as well for you guys to study. Longitude is, imagine that same line, and what angle does it make relative to the prime meridian, which goes through Greenwich, England. If you're going east from there, it's a positive angle. If you go west, it's a negative angle. So latitude can range from negative 90 to positive 90 degrees, South Pole and North Pole. And lines of latitude are also called parallels because they're all parallel. Right? And longitude can range from negative 180 degrees to positive 180 degrees as you go around the circumference of the Earth. And negative 180 is exactly the same as positive 180. It's on a point on the opposite side of the Earth relative to the prime meridian. So lines of latitude are also called parallels. Lines of longitude are also called meridians. And so that's just, so picture in your mind, what are these angles? That's what they represent. So this point is 39.430875 degrees north latitude and 77.805836 degrees west longitude. Okay, so you could also, you would see this as then, well, that's positive 39.430875 and negative 77.805836. So you have positive because you're going north and negative because you're going west in the prime meridian. So when you see latitude and longitudes represented like this is called decimal degree, which should make sense. It's degrees in decimal format, decimal degree. But you'll also see, change color here, you'll also see latitude and longitude reported in what's referred to as degree, minute, second format. And so this, whether there's a connection between the minute and second we use in time, is maybe there is, but it's irrelevant because we're not talking about time here. We're talking about angular units, measures of arc. And but it's interesting that there's 1 degree is 60 minutes, and 1 minute is 60 seconds. So the way that you would go about, you could convert back and forth between decimal degree and degree minute seconds, and the way you do that is by using this factor 60. You either multiply or divide by 60 to go back and forth between the two. All right, so let's do an example here to show you how you could do this. So I really, I expect you guys to be able to do this at least once, but let's just look at the 39.430875 degrees. So the way you would convert this to degree minute seconds is, well, the degree part is easy. You got 39 degrees, okay, and then you got this remainder, 0.430875, and that's a fraction of a degree. So what you would do is you figure out, well, how many minutes is that? If one degree is 60 minutes, multiply 0.430875 by 60. So you multiply we'd multiply the remainder after you take out the whole number of minutes. Multiply that by 60, and you get 0.430875 times 60. You get 25.8525 minutes, and the symbol for minutes is that little hash. So we got 25.8525 minutes. That's equal to 0.430875 degrees. So we take out the whole number of minutes, and what we have left is this fraction of a minute, and we multiply that by 60 to figure out how many seconds that is. And that becomes 51.15, and 2 hash marks is seconds. So we round. It's customary to round seconds to the nearest whole number. So which of these is more precise? Decimal degree, you can have more precision. Which one is more common these days? Decimal degree, but you'll see it both ways. So in other words, 39.430875 is approximately 39 degrees, 25 minutes, and 51 seconds. Okay. If you're going the other way, instead of multiplying by 60, you will divide. So you're like, how many? Ooh, that's weird. What the heck's going on? Get rid of that. Well, maybe we'll do an example of that on another day when I actually have a real coordinate to give you. But there's, you would say, well, 51 divided by 60, that would recover the decimal degree associated with the minutes, and then to that you'd add 25 to figure out how many total minutes you have, and then divide that by 60, and then you add that to a 39 to give you the decimal degree. So you lose some precision when you write it as degrees, minutes, seconds. And the reason is, here's a fun fact. You ready for some fun fact? You ever hear of the term nautical mile and wonder what that is? Nautical mile is not the same thing as a regular mile. 5,600 feet, or whatever that is. So here's a fun fact. 1 nautical mile, what the heck is it? Is equivalent to 1 minute, so that's 1/60th of a degree of arc along any longitude, any meridian. And it turns out that that's equal to about 1,852 meters, or 1.15 miles. So if you're traveling along a longitude, you're traveling along a longitude on the surface of the Earth, and you travel 1.15 miles, you've gone 1 nautical mile, which is 1 minute of arc along that line. And so there's 60 minutes in a degree and 90 minutes going from equator to the North Pole. So a nautical mile is a little bit longer than a regular mile, a normal mile. Well, let's keep going. So if you divide that number by 60, so there's 60 seconds in a minute. So if you divide this number by 60, then 1 second of arc as you travel around the globe is approximately 31 meters, which is about 101 feet. Okay, 30 meters or 101 feet. So here you can see that when you have a location that's reported to you in degrees, minutes, seconds, if the seconds are rounded to the nearest whole number, the most accuracy you can have is you're within 30 meters or 100 feet. No, I guess you have to divide that by 2. So you're within 50 feet or 15 meters of where your location actually is. So there's a limitation in accuracy there. So that's an advantage of decimal degrees. You can be more accurate, more precise. So, all right, let's let's take a look at. Let's see if I can do this. I'll hold it up first. All right, so let's talk about compasses. So the compass here has it has the compass needle. And it's not going to work when I hold it up like this, but when I hold it flat, the compass needle is a little magnet, and it lines itself with the Earth's magnetic field. The part that points in that direction is pointing toward magnetic north. So in magnets, it's actually opposites attract. So it's actually a south pole here of this magnet is pointing toward the Earth's north pole on its magnet. So the Earth is a giant magnet, and this is because of the way the dynamics of magma flow in the Earth's mantle, and it's pretty cool that the Earth is a giant magnet. So the compass points you toward magnetic north. Okay, magnetic north. And if you look at, let's go back to here. So you're looking down on the compass. You got the compass dial, and the compass dial, and it's got the compass needle, And usually the part that points north is colored red, and the other part is just, the other side is just black or white. And so you got this thing that's pointing toward north. And if it's a compass, it's pointing toward magnetic north. And it's really important to understand that that is not the same, that is not equal to geographic north. Okay, it's not the same thing. And all right, so we'll get back to that. But when you're working with a compass that's pointing toward magnetic north, the compass dial, it breaks up the directions of bearing into 360 degrees. So 90 degrees is east, 180 degrees is south, 270 degrees is west, and 0 degrees, or 360, since you're back to where you started, is north. So you can, when you use a compass, you can determine a bearing. Let's say you want to figure out which direction you're traveling, which direction you're walking or traveling. You can figure that out as a bearing on the compass relative to the direction of the north arrow points. And so you report that bearing in one of two ways. You could report it as just this angle. It's called an azimuth angle, or bearing. Or you could report it as something called a quadrant bearing. Okay, sorry, I'm writing kind of small here. And what I mean by that is, if you think of the circle here, you could break it up into 4 quadrants. Quadrant 1, quadrant 2, quadrant 3, or quadrant 4. And the direction is going to be in one of those quadrants. You can always go back and forth between the two. I'll give you some examples here of what it means. So if someone tells you their bearing is 90 degrees, what is that? That's equal to quadrant bearing due east. Write out the whole thing. If they tell you their bearing is 120 degrees, well, now you're down here in quadrant 2, and you might say, well, that's somewhere between east and west and south. Somewhere between east and south. And the convention is that, so let's draw it in green here. So 120 is somewhere around here. That's 120 degrees. So you could say, well, that's 30 degrees from due east, or it's 60 degrees from due south. And you might say, well, it makes sense to specify that quadrant bearing relative to the closest cardinal direction. And but the convention is something different. What you do is you always start with either south or north. So this azimuth bearing would be south, and then go 60 degrees back east. So that's how you would represent that that bearing. So let's do another example. And I used the word, but I didn't really define it. So the directions north, south, east, or west, they're called cardinal directions. Okay, north, south, east, or west. All right, let's do another example. How about 290 degrees? Can you figure out what it is? If I convert it to quadrant bearing, so 290 is somewhere right here. So we always start with north or south. It's closest to north, so we'll start with north. So if you're going north, you got to come back 70 degrees toward the west to get to azimuth bearing 290. All right, so I just wanted to point out that you can go back and forth between these, but bearing is always, so what is this? It's important to understand that these compass bearings, they're measured in degrees. It has nothing to do with latitude and longitude. Nothing at all to do with latitude and longitude. They're two completely separate things. All right. Latitude and longitude have to do with your location on the surface of the Earth relative to these lines, these hypothetical lines that emanate from the center of the Earth. All right, from the center of the Earth to a point on the surface, the angle that line makes relative to the equator in the prime meridian. Okay. Compass bearing, it has to do with how a compass needle, a little magnet, aligns with the Earth's magnetic field. And and one way I can convince you that compass bearing has nothing to do with location is that if you're at a specific location, you could hold your compass up and it's going to point north, but you could go in any direction from that point. So you could take a bearing in any direction. So there's no bearing that's attached to any particular point. And the other way around, if I'm following a specific bearing on my compass, I'm going to move through, across the surface of the Earth, and I'm not going to stay in the same location. So you can have the same compass bearing in multiple locations. All right. So they have nothing to do with each other, even though they're both measured in degrees, because we're dealing with things that are represented using circles and spheres, and the way you represent things that are circular or spherical and arcs and things like that is with angles. Okay, so that's the connection. Here's you want another fun fact? Okay. Remember, so one of our projections that we like is called the Mercator projection. It's this rectangular projection projected onto a cylindrical surface. And I said that one of the properties of the Mercator projection is that any line that you draw on that map is a line of constant bearing. And which means that if you stayed on that line, your compass, if you had a bearing on your compass and stayed on that bearing, you would stay on a straight line on that map. Okay, so here's something that's really weird. If you actually did that on the curved surface of the Earth, if you actually had a compass and you said, okay, I'm going to keep moving in this direction, I'm going to keep moving on this bearing, the actual path that you would take around the surface of the Earth is called a RHUMB line. RHUMB, RHUMB. Let's see if I can draw this. So RHUMB, RHUMB line. And what this is this is a line of constant bearing. So that's constant direction as measured on a compass. And the property of a line like this is that every time it crosses a meridian, it's going to cross at the same angle. So it crosses meridians, lines of longitude at the same angle. And with the Mercator projection, that should make sense, because on Mercator, the latitude and longitude lines make a rectangular grid. So if you're going in a straight line, you're always going to cross the longitude lines at the same angle. But if you actually went to see, well, what does this look like? You know, here's the Earth, right? Here's north. So we got meridians. It's going to be really bad. Well, that's not too bad. Well, that last one was pretty bad. Got these meridians. And if you're on a path that crosses these meridians at the same angle, the path is actually a spiral that spirals in toward the north or south pole. So rung lines, lines of constant bearing, are spirals like this on the surface of the Earth. It's weird. But it's still useful navigationally because it's easy. The easiest place to get between one place and another on the surface of the Earth is not necessarily a straight line if you need some way to tell which direction you're going. And if you're using a compass, following a constant bearing might be the easiest way. All right, just another little fun fact. So here's another. This is another thing that's weird about navigation is that if you're using a compass for navigation, the compass tells you magnetic north, and that is not the same thing as geographic north. So on a GIS, on a map, geographic north is north. It's going up to the pole. And but magnetic north points toward the place on the planet where Earth's magnetic field has a north pole. And they're not the same. They're not the same. In fact, where we live in West Virginia, the difference between those, if you're looking at a compass, the difference between the direction the compass points, which is magnetic north, and true north is around 10 degrees. 10 degrees. So this difference is called magnetic declination. And let me write some stuff down on this. Magnetic declination. And so you actually, I didn't write that very well, you'll actually see this on a good map. A good map will include this. So what it'll have is it'll have a compass rose somewhere on the map, and it'll be like, there'll be a line showing north, and then there'll be a subscript or some indication that this is magnetic north. And then there'll be another line that is labeled north, and it'll be geographic or just N or true north. So you'll be shown both, and then there'll be an angle given between the two. I'll label that delta. So delta is when it's greater than 0. That happens when magnetic north is to the east of true north, geographic north. And if delta is less than 0, that happens when NMAG is west of true north. So for here in West Virginia, if you look it up, the magnetic declination here is negative 10.41 degrees. Okay, that means it's negative, so that means the declination is 10.41 degrees west. Okay, so for us here in West Virginia, your compass, this is the direction your compass points. True north, geographic north, is actually this many degrees well, moving clockwise from the direction you're looking. So this is, I tell you, this is a pretty important thing for cartographers, and one place that you guys will probably run into this in your own lives is when you're looking at the work of surveyors. Like you're going to buy a property and you see it. I have one around here somewhere. Let me see. I don't know if you guys can see this, but this is a plat. So this is a map that a surveyor makes showing the boundaries of different properties. And if the surveyor was careful or did a good job, they will show you on the map. They'll tell you first, okay, here's north, and they'll tell you that's true north as determined by some parameters, or it's magnetic north. And if they tell you it's magnetic north, that's better than nothing. But here's the really weird thing about magnetic north: it changes. So your compass, the direction it points today may not be the direction it points a year from now. The magnetic North Pole is moving around, and so here let me show you. I looked up some actual numbers. Here in West Virginia in 1990, so that's 30 years ago. Back when I was much younger. The magnetic declination was only 9.44 degrees west, and now it's almost a whole degree more west. And in 1776, in the beginning of the Revolutionary War, the birth of our country, magnetic declination, our best guess is magnetic declination at this point in what was then Virginia, was 1.5 degrees west. So it's moving. I found a cool website. Let's see if I can bring this up and show it to you. This will be the last thing we do. So we'll do feature creation on Monday. All right, good. My browser open. So I'm gonna type in the URL here. I wrote it down. It's maps.ngde noaa.gov/viewers/historical declination. See if that works. Oh, come on. Oh, let's try the Googles. Actually, let's try DuckDuckGo. I'm gonna spread the wealth. I'm trying to use DuckDuckGo more. Historical declination, NOAA. I just forgot something. Okay, so actually this projects into the future where it's going to be. So we're looking at this is the Earth projected in Mercator, and so everything's rectangular. And so in this map, up is true north, down is true south. So here, let me see if I can zoom into, here we go, into the United States, eastern half of the United States. So there's a line here in the center of the country. It goes through Louisiana and up through, I don't know, Missouri, Iowa, where north on the compass is true north. But over here in West Virginia, you can see that declination is about 10 degrees west of north. And over here in the western United States, declination is east of north. And the reason that this is happening is because the pole keeps moving around. Let me show you. Let's switch to an Arctic view. All right, we're looking at this planar projection of the Arctic. Can I turn off? Let's turn off the lines for a minute. Okay, and if I use the slider, the pole, go back to 1700, and the magnetic north was in northern Canada, and now the magnetic North Pole is migrating closer to the actual geographic North Pole. All right. But as early as the 1990s, the magnetic North Pole was basically in northern Canada. So it's moving around. It's moving around. That's crazy. Let's look at the South Pole. I wish there was an animation that would just play. All right. So one more thing. We know this from studying rocks that were formed in the past. That when these rocks were formed, there was an imprint of Earth's magnetic field at that time. So by studying the orientation of components of these rocks, we know that the magnetic pole of the Earth has gone through reversals in the past, where the North Pole has flipped and become the South Pole, or the South Pole has flipped and become the North Pole. And so this happens every, I don't know, a couple, 50,000 years, 100,000 years. And it appears like it happens pretty quickly. So when it happens pretty quickly. All right, and meaning quickly, meaning in geologic time, not human time. Although it would definitely be noticeable in the time scales of humans. And we also suspect that during these times when the magnetic pole is reorganizing and flipping, there's more than one. So there's more than one magnetic North Pole and more than one magnetic South Pole. It's like the Earth's bar magnet has broken into little pieces, and it takes a while to realign. So how cool would that be if we lived during a time like that, where your your compass might be spinning and not be very useful? All right. So you guys have a good weekend. Anybody have any questions before we call it a weekend? I don't see any in the comments. So I guess we're good to go. All right. I will see you guys next week. Have a great weekend.